Hey there, welcome back to another video for Math 2241. And today we're going to talk about vectors. Now, this is going to be a very large section. There are a lot of terms and a lot of formulas. Luckily, a lot of them are very similar and they're just slight variations of each other. But we will walk through everything very slowly, okay? I'll try to do this as clearly as I possibly can. So we're going to talk today about vectors. And let's just take a look at our terms beforehand, and we'll just read through them to get familiar with what they are. So we have vectors. We're going to talk about displacement, initial and terminal points, the zero vector, the vector sum and difference, scalars and scalar multiples, parallel and antiparallel, negatives of vectors, components of vectors, representations and standard representatives of vectors, magnitude, length, and norm, they're all the same thing, n-tuples, standard basis vectors, unit vectors, and resultant forces. So that's a lot going on. We'll walk through those on the next page. Next up, we want to talk about these formulas right here. So when I write down this thing u vec and v vec, there's a little arrow above. Technically, that's like an up harpoon arrow. If you use LaTeX, you'll know what that is. We've got u vec and v vec here, and they're written as points in R3 with coordinates u1, u2, and u3, and v1, v2, and v3. All right, so what are we looking at here for the formulas? Well, we're going to talk about what the vector sum is. So we have the geometric formula that says, all right, u plus v is the vector pointing from the initial point of u to the terminal point of v. You can think about that intuitively for now. We'll draw some pictures on the next page. And then these equations are expressing that same statement. The algebraic sum, where we take these coordinates and add them up coordinate-wise. So u1 goes with v1, u2 goes with v2, u3 goes with v3. All right, now we're talking about scalar multiples. We have the geometric version. So r times u has the initial point that's the same as u, but has length r times the length of u. And also, I forgot to mention, if r is a negative number, then we swap the direction of the vector u. And we'll see more of that on the next page and in the examples. The algebraic version just says, all right, take the components of this vector and multiply each one of them by r. So these components u1, 2, and 3 are real numbers, so is r, which means we're allowed to multiply those together. The magnitude, length, or norm is represented by this symbol. Here's the formula for it. Notice that it is literally just the distance formula rewritten. It tells you how long a vector is. Okay. So now we're getting into some more complicated stuff. We have the formulas for the standard form of a vector between 2 points. So the idea is that we're given these points P1 and P2, and we can organize them into an ordered pair. So P1, P2, and I expand those two into these triples. And I tell you that these two things are the same, quote unquote. That's why I use this squiggly equals. If, well, I look at the difference between the coordinates x1 and x2, y2 and y1, z2 and z1, and I look at that for p1 and p2, and then I also look at that for q1 and q2, and I end up with the same number for both p and q. Basically, this is just saying that both this vector and this vector need to point in the same direction and by the same amount for each coordinate. Okay, and then I tell you, all right, well, u, the vector u, is all of these pairs of points collected into a bag, and then I just use this one right here as a way of representing u. So when I write down a vector u, I will be talking about this one, but really all of this is going on in the background. And what this means is that it doesn't matter where I draw a vector in space. They are all going to be quote unquote the same vector. So I can move them around and get the same answers regardless. Okay, so we'll see more of that again in the definitions of terms and the examples. Standard basis vectors are one way of referring to vectors in coordinate form. They're kind of like primes. So we have I hat, j hat, and k hat, and they're written as triples, 1, 0, 0, 0, 1, 0, 0, 0, 1. And we can write any vector in R3 using as a sum of these guys. Technically, it's called a linear combination, and we'll see what that means in a minute. Unit vectors are vectors with magnitude 1. Total force is a physical thing, but it is basically this equation. If you look at all of the forces acting on an object, like gravity, tension, maybe there's a spring force, the total force at any time is just the sum of all the forces that are acting on an object at a certain time. So maybe if you're sitting in your chair, you can think that gravity is acting on you, pushing you down into the chair. But you don't fall through the chair because the chair is pushing you right back up with the same force as gravity. Okay. And then we have vector algebra. So this is telling us how to do algebra with vectors, essentially. And you'll notice that some of these are very familiar. We have the commutative rule. You can swap addition. The associative rule. You can move parentheses around. There is a zero vector, which doesn't change anything, just like adding 0 does nothing to a real number. There are inverses. So if you have a vector and you add its negative to it, then you get the 0 vector back. You sort of just rearrange this equation right here. And when I say negative of a vector u, I mean -1 times u. For 5, we have that if you scale a sum of 2 vectors, that's the same as scaling each vector and then summing. If you scale a vector by a sum of 2 numbers, that's the same as scaling the vector by each number first and then adding the results. And then over here, we have sort of an associative rule. You can scale by a number, or you can factor that number and then scale by each divisor independently. And then last is that multiplying by 1, scaling a vector by 1 doesn't change it at all. So those are our formulas. I know there's a lot there. Go back through the video if you need to see anything again. And we'll go over our objectives here very quickly. So we have easy, medium, and hard again. Easy, I want you to know what a vector is geometrically and algebraically. I want you to understand the connection between vector geometry and algebra. So we're going to talk about how to look at vectors as arrows in space, and then how to add them as lists of coordinates. Medium, I want you to be able to comfortably do the geometry and algebra with vectors. And then down here, what that means is to add, subtract, and scale vectors, both visually and in coordinate form. And then I also want you to be able to calculate vector norms. It's a bit of an annoying formula, but it's really important to know, and it gets used all the time. The hard objectives are to understand that formal construction of vectors, this whole thing up here with like the standard form and all of this. That is something that you can ask me about in email if you want. And I might add that into the explanations for this video. Last is to be able to translate physical problems into problems that are solvable by vector methods. So we'll do an example of this as the last problem in our examples video. But basically, I want you to be able to read some sort of problem, recognize that vectors are useful for solving it, and then be able to write down some sort of vector function or equation that gives you a way to get to the answer. All right, so that's our first page here. Let's go to definitions of terms. All right, so what is a vector? A vector is a lot of different things. The simplest thing to think about it as is probably an arrow in space. So get my straight line tool out here and then draw an arrow, and I'll label this guy U vec. And this now is a vector. Vectors can be moved around in space. So if I take U and actually let's do this. I'll copy and paste it over here. I do not have to change the label on this right here because these two things are the same vector. If I were to take this guy and rotate him a little bit, so rotate them, now they're not the same vector, they point in different directions. So I'll undo that, and then we'll think, let's draw a different vector in actually. Let's get rid of this guy, and I'll draw a new one. Now we have this vector over here, pointing in a different direction, we'll call it V. Okay, so this is another vector, it's an arrow in space that starts at one point and ends at another. Okay. Another way of thinking about vectors is algebraically. They are lists of points, U1, U2, and U3. Same for V. Let's put that in white, make it a little more visible. There we go. So they're lists of points. And the idea there is that you have an implicit XYZ coordinate system hidden somewhere in the background. And you can think of the vector U as being extended from the origin to some point with those same coordinates. And we'll put that point in right there. So this vector U is the same as, quote unquote, that point in R3 space. All right, so next one is displacement. Displacement is a way of talking about a change in position. It's the net change in position. So if I were to start at some point, again, pretend we have an XY. Yeah, we'll just do XY. So X, Y, coordinate system here. And let's say I start at this point right here, P, and I walk over to this point, Q, right here. Then I can call this thing, this arrow that I just drew, the vector PQ, and that is the displacement vector from P to Q. But let's say I do that, and then I walk over to here. And I want my straight line tool here. And we'll call this point R. And this will be the vector Q pointing to R. All right, well, my displacement vector from P to Q, we already have, and my displacement vector from Q to R, I have. What about my displacement of overall? How has my motion changed, or my position changed from P to R? Well, I could also just have drawn a straight line from P to R. I didn't have to do the trip to Q first. So this is the vector P to R. And that is my total displacement vector over the entire trip. So I walked this way and then this way, but I could have also done this, and that would be my total displacement. In one dimension, you can think of walking from P to Q, and then maybe you walk back a little bit. So let's say this is 5, this is 2 backwards. So I add 5, subtract 2. My displacement would have been 3 from my initial position. Okay. And I also want to mention that displacement can be negative in that sense. So if I were to walk from P to Q in 5 units, and then Q back to, let's say, S over here in -7 units, my displacement would be -2 from my initial position. All right, and so that leads us directly into initial and terminal points. We'll draw another vector here, and we'll do a little analysis of this vector. So here's my vector u, and right here, where it starts, this is called the initial point of u, and I'll notate it that way, init u vec. And then the point where the arrow is the terminal point, and we'll call it term u. So for a vector visually, init is just where it starts, and term is where it ends. This is also sometimes called the head and the tail of the vector, or the tip and the tail. And sometimes you'll hear vector addition be called the tip to tail method or something like that, or visually it's called that. All right, next is the zero vector. So if I were to draw an arrow pointing in one direction, we'll call that u, and then have another arrow pointing in exactly the opposite direction. Here we go. Okay. Then maybe this is v. The displacement vector is 0, right? I've made no change in my position overall. I might have walked from here, P, to here, Q, but then I walked straight back. And so my overall position is 0. So the vector P to P equals the 0 vector. And this vector has no direction. I just started walking in one direction and came back. I could have walked in a different direction and then come back. I've walked straight up and then straight back down. And I would have gotten the same vector. So the 0 vector does not have a direction. Oh, and that reminds me that I needed to give you actually one more description of a vector. A vector is something that has a magnitude or size, length, norm, whatever you want to call it, and caps a direction. And this direction here, that's the part that makes it a vector. So regular real numbers, you can measure the size of by using like the absolute value, but vectors tell you a direction. And this in, again, one dimension would be like saying, is the number positive or is it negative? You only have one direction to worry about in the real line. But in like 2 dimensions over here, you can say, all right, is it going up, down, left, right, or, diagonal somehow? So you can have honest vectors in 2 dimensions and even more complicated vectors in 3 dimensions up there. All right, so the 0 vector is something that has magnitude 0 and no direction, weirdly enough. It's the only vector like that. Right, what about the vector sum and difference? Well, you've already seen how this works. Up here, you walk in one direction, and then you walk in the other direction along that vector v, and we got the 0 vector. This would be like saying that u plus v equals 0. And by one of those vector properties, if you go back and look, this actually implies that v is the negative of u. So we are already defining something a little further along there. But let's go ahead and draw the vector sum and difference in general. So if I'm given a vector u and a vector v, let's draw those like that, u, v, and I want to add them together. Well, there's a way to do that visually. There it is. So we're going to copy, paste, and move this guy. So this is what I called the tip to tail method. So you put the vector v at with its initial point at the terminal point of u, and you just say, well, what's the easiest way for me to get from the start of u to the end of v? And I'll draw that straight line directly between them, and that is the vector sum of u and v. All right, what about the difference? Well, I kind of have to cheat and tell you what the negative is ahead of time. But if I want to do the same thing here, paste that again, then I take v, and I'm actually going to flip it around. So we're now going to say v points in that direction, and this is minus v. If you want, you can also just think of a vector pointing in the opposite direction of v. That's fine too. And we do this. Move things around a little, make it clearer. So now I have starting point u, middle point, tip of u, and then go to the tip of v. And my vector difference is going to be the arrow pointing from the start of u to the end of v, and this is u minus v. Okay, and so that's how that works there. All right. Next is scalars and scalar multiples. So a scalar for us is just going to be a real number. There are more general types of scalars, but in this case, all we really need is some way of multiplying the size of a vector, but keeping its direction. And that's what the scalar multiple is. So if we now take a vector u again, so here's my vector u, and let's actually make this a little bit different. I want that vector to be slightly smaller, easier to scale. We'll do this. Here we go. So now I take this guy and I copy, paste it over here. Remember that we can move vectors around in space and they don't stop being that vector. They just end up starting and ending in a different position. And this vector now is, let's say, twice the vector u. So I move in the same direction, but I go twice as far. And it doesn't matter where I start. Okay, now what if I want to go the other direction? Well, again, I copy paste u, and let's say I want to go 3 halves, 1.5 times as far, but in the opposite direction. Okay, well, this is going to be minus 3 halves times u. Maybe that doesn't look exactly like 3 halves, but you can kind of imagine the idea there. So this is scalar multiples of vectors and scalars themselves. The scalar is this number 2 right here, the hidden number 1 right there, and the number -3/2 there. And the scalar multiple of the vector u is the whole vector 2u, or -3/2 u. All right. So parallel and anti-parallel vectors. If I have a vector u, a vector v, and another vector w, let's put w over here maybe, then let's say w points in that direction, u points in that direction, v points in that direction, u, v, and w here. We say that u and v are parallel, and we can write this symbol, a little double bar in between them, and u and w are, let's put that in white right here, parallel, and u and w are anti-parallel. That's not quite what I want. Let's put a little star on this for anti-parallel. Oh, you know what? Actually, this is better. Sorry, I'm making up this notation on the fly here. It's not standard. We'll say u and v are parallel, and we'll have an arrow, 2 arrows pointing up, and u and v are anti-parallel. Will be 2 arrows, but pointing in opposite directions. That's much better. So u and w are anti-parallel there. Parallel, anti-parallel. Note that it is possible for vectors to be neither parallel nor anti-parallel. How do we do that? Let's just put a weird vector in here. It does something like that. Okay, this is now our vector. Let's call it A. So A is neither parallel nor anti-parallel with any of these vectors, but in particular with u. U, and we'll put parallel, anti-parallel, and we'll say it is not parallel, not anti-parallel. So we'll just put a slash through things if we want to say it's not true. Okay, we've already seen this, but just to put it in formally, a negative of a vector, if we're given u here, a negative points in the opposite direction, and we can actually just put these at the same starting point. Make things a little clearer, hopefully. So here's our starting point, and our vector u points in that direction. Our vector minus u points in the opposite direction. Given what we just wrote down for parallel and anti-parallel, u is always anti-parallel with minus u, and u is always parallel with itself. So just good things to note. All right, going on to the next term, we have the components of a vector. So now we're starting to talk about algebraic stuff. The components of a vector u, we need a coordinate system to be defined. So we have x and y, and then u is thought of as being embedded in this system. We have a line here, and u starts at this point, ends at that point. And we say, all right, well, remember that we can move vectors around, so we don't actually care all that much about these points. We can take this vector u, put it right there, and then I'm gonna switch to yellow for this. We can see, well, the coordinates of the end point here are whatever they are, and the coordinates of the beginning point right there, are the origin, so 0, 0. So we'll mark that. This is the point 0, 0. And this is the point u1, or maybe we'll call it ux for this example, ux and uy. So ux is just the length in that direction, and the length in the vertical direction is uy. uy, ux. Note that these can be negative and point in the opposite direction. And so we can think of the component lengths or the component vectors to get from the starting point of u to the ending point of u along the x and y directions. We could use different directions or different coordinate systems if we wanted. Note that this format right here depends on where I place the x and y axes. But then we do this thing where we write down the vector u itself as the coordinates of the terminal point, where it's implicit that the initial point is at 0. So that's what we mean when we say that u has these coordinates. Because again, remember, vectors can start and end anywhere in space. We can move them around and they're still the same vector, but the coordinates of the start and end might be different. So really what we're caring about here is the difference between the start and end coordinates. That's what makes something a vector. And these things right here are our components. All right, so representations and standard representations, or sorry, representatives. Representatives. This is what I was talking about. We have the vector that I want in blue. I call it u again. And if I copy and paste this into various places in space, these are all considered the same vector, even though they're placed in different spots with an xy coordinate system drawn in. Y, x. These are all starting and ending at different points in xy space, but u, the vector, is the difference between those starting and ending points. And so really, we have the same type of arrow no matter what, or no matter where we start it in this xy plane. Now, the standard representative, because we don't want to have to deal with, okay, where does the vector start, or what's my starting and ending points? To do algebra, it is a lot easier to just set the origin as our starting point, like we did up here, and let me copy paste that again. Come on. Now, there we go. Okay. So now this right here, this is our standard representative. Standard rep. And that's because the initial point is at 0, 0. So standard rep means that the initial point of u is equal to 0, 0, or in R3, 0, 0, 0. All right, so now let's talk about the magnitude, length, or norm. So note, if I draw another coordinate system in here, told you we're going to deal with coordinate systems quite a lot here. And I draw my vector. In fact, let's put in our z coordinate as well. Here we go. Now we've got x, y, and z. And this is our first three-dimensional vector. Let's say u starts at this point and ends at that one. There's u. And starting point, ending point. Let's make this a little bit more 3D looking. You can see what I mean here. Here's P, here's Q, and maybe P is way back here, and Q is way up there. So U is pointing sort of towards us and down. Well, the length of U is just the distance between P and Q. That's why it's written that way. So we have that the length of U is equal to the distance between P and Q. This is also the distance between the initial point of U and the terminal point of U. Okay, and then because we already know the distance formula, we have that this is the difference in the x coordinates squared plus the difference in the y coordinates squared plus the difference in the z coordinates squared, all square rooted. But we know what those are. Those are the components of the vector. Because remember, the vectors are the differences between the terminal and initial points, not the points themselves. It's a bit weird to think about, but you'll get used to it after a while. Okay, so an n-tuple, this is a little easier. An n-tuple is just a list of coordinates. So maybe if I write, actually I don't want to use x there. So U as a vector, well, I could also write, now we'll just leave it as a vector. So an n-tuple is just a list of real numbers. And I do want this to be an ordered list. So there's a first, second, third, whatever, and so on position. And we have n positions. So maybe n is like 17 or 104 or 563. It could just be any list. So this is an n-tuple. Actually, maybe let's mark the first, second, third, and so on positions. We've got our 1, 2, 3, and so on. And then n is our last position there. Okay, so standard basis vectors are next. And these are ways of talking about vectors in space using that standard representation. And these are sort of like primes. I mentioned this before for vectors. So we have I hat, j hat, and k hat. And these guys, I'll rewrite the formulas here. 1, 0, 0, 0, 1, 0, and 0, 0, 1. And in an XYZ plane, or sorry, space, these guys sort of look like this, X, Y, Z, and then in red, I'll put, that's not very visible, is it? Maybe I want this to be white for now, sorry. That's probably a bit annoying. Here we go. Now I can put them in red. So here's my I vector. And my j vector and my k vector. I hat, j hat, k hat. Sorry, that's still kind of hard to see, isn't it? Well, just bear with me. And these guys are called the standard basis vectors because they point in the directions of the basic axes. And they are standard. They start at the origin right here. The other thing about them is that they have length 1. So if I were to take I hat and compute its length, the norm of I hat, remember that this is the square root of the square of the first coordinate plus the square of the second coordinate plus the square of the third coordinate, 3. All right. But if I come back over here and look at I, its definition says that's the 1 plus 0 squared plus 0 squared Well, pretty clear that that's going to end up being 1. Okay, so these guys have length 1. And that leads us directly into our next definition. A unit vector is any vector with length 1. So these vectors can point any direction they want. They just have to start and end at points that are one unit away from each other. This also, if you talk about the set of all vectors u, so that the norm of u is equal to 1, this is also a way of defining a sphere. Why is that? Well, because if I unpack this definition, or this norm definition a little bit, what do I get? I get u1 squared plus u2 squared plus u3 squared equals 1 squared. And that is a sphere of radius 1 and centered at the origin. Well, I guess the centered at the origin part is if we're assuming these are standard vectors, but that's what we want. All right, last but not least is the resultant force. And this is going to be a little bit trickier to think about, but if you've taken some physics, maybe it'll be familiar to you. What we'll have is, let's say, a box of some mass. Switch. Mass, whatever, m. And we have some forces acting on it in different directions. So let's say I push the box in that direction. This will be my force 1. Now, note that I called that a vector because it has a force, a magnitude, how hard I'm pushing it, and in what direction I'm doing that. Well, now let's say that somebody else comes along while I'm pushing this and tries to push the box in the other direction. Well, how is the box actually going to move when we're both pushing on it? It's going to move in the same direction as the sum of these two vectors. Let's copy paste and do our vector sum. This actually. Then we'll copy paste. And let's see, paste, blah, move. And here's another way to do vector sum. It's called the parallelogram rule. Instead of the tip to tail method, you, actually, let's just paste this again. This will make my life a little bit easier. So it's basically the tip to tail method, but you draw a different shape. So start here, and we get our resultant vector. That's what this is called, the resultant force. And the resultant force is exactly the direction and size that the box will end up moving when both myself and the other person are pushing on it. So this is how the box actually moves. How box actually moves. All right, so that is all of our terms. I know there's a lot of them. Go back through the video and redo any of the ones that you are uncomfortable with, and then join us in the next video for some examples of working with vectors.